introduction, but I'll introduce him anyway. Turing Award winner, Alan Kay, is here with us today. He's coming to visit us for our CS, or for HS workshop tomorrow, but we figured while he's here, we'll pick his brain a little bit, get some ideas of what he thinks about the current state of CS education and where he might go with CS education. And what we'd like to do is allow you to ask him questions. He wants to pick our brains as well, so what we kind of think where things are going as well. So he may throw some questions back at us as well. Right, but did you want to make a few opening comments?
Well, I think that maybe the...
He has one.
I have one, but maybe it's not on.
That might be for the
Okay. Sure. An old... I guess with two mics we should have at least two opinions. I think this one works. Hey.
For now, I'll steal from him later.
This will probably be too loud. Okay. Well, an old friend of mine, Neil Postman, who's written many interesting books about media, when he was a graduate student in the 50s, he and a fellow graduate student found McLuhan, who was just starting to write some interesting books about the ecology of interaction between human mental systems and the representation systems that they use. And they just, being graduate students, being the 50s, they just followed McLuhan around to see what he would do. And Neil Postman had many interesting stories about McLuhan, but the one I liked the best was that when McLuhan would give a talk, if somebody got up and started arguing with him, McLuhan would never argue back. He would just say, well, how about this one? And give him another idea. Because McLuhan viewed what his job was to get people thinking about things that they hadn't thought about, or things that were paradoxical and thus maybe didn't go together, and McLuhan thought they should go together. But he actually wasn't trying to convince anybody of anything. So he called these ideas of his probes that were just, and I'm not sure, I think my opinion of computer science education in university, first, is not important, but second, I think whatever opinion I have is probably too limited to even put forth a claim that would be accurate. I will tell you that about 5 years ago, I started a nonprofit research institute called Viewpoints Research Institute, because I finally just did not want to try and do research inside of a company anymore, and the ARPA funding had run, the good ARPA funding had run out actually even before Xerox PARC had started in 1970, and the NSF has always been pretty chicken about funding computing, except for rare instances when somebody from our field, like Gordon Bell, went there in the late 70s, primarily to force NSF to fund the internet backbone. If he hadn't done that, we wouldn't probably have an internet today. So, but generally speaking, the funding situation has not been good. Now, to most of the people in the room, the funding situation is normal, because you grew up in that funding situation. And to me, who started in the early 60s, and we knew, believe me, we knew things were good in the 60s and the 70s, because they just really were good. And even though it was normal for things to be good. But looking back now 25 years to the end of this, sort of in the late 70s, just how good they were in the 60s and the 70s was astronomical compared to what we have now. So there are many, and I believe that a lot of the problems in computer science education have to do with scale on the one hand, the commercialization of a lot of inventions that were done in the 70s, and hence a lot more jobs. Nice thing about computing in the 60s and the 70s was you couldn't really make a living at it, and so it attracted people who were actually interested in computing for itself. And most of these people actually had considerable training in disciplines that were well established. And so their bullshit detectors were very, very good. I think computing has a real problem in that I believe it's not yet a field. When Perlis made up the term computer science, he meant it as an aspiration. I think it was a great aspiration. I think it was getting going. I don't think we don't have some of the normal positive trappings of a science. So I don't think that has happened yet, and there's an infinite amount of detail that we can spend whole college careers learning without learning anything particularly interesting or enlightening or forward-looking. So I think that is a real problem, and there's nothing like detail to attract people who design curriculum. Right? So go to a neutral ground. If the problem were music, a curriculum designer with the charge to design a curriculum for everybody in music would undoubtedly pick something like the C major scale to teach, because you can test it, can be memorized. It has nothing whatsoever to do with music. When I was learning to play pipe organ at UCLA in the early 80s, I got to watch the performance major at UCLA being phased out in favor of musicology. And the reason was not even UCLA, but the entire University of California wanted papers. They wanted certification that they could look to nationally, and you could not write a lot. There's not a lot you can write about performing. So there's this great story about Schumann when he played a piece and somebody came up and asked him a question about the piece, and Schumann sat down and played it again. There's a great line attributed to everyone from Stravinsky to Frank Zappa that talking about music is like dancing about architecture. And so I think that Marvin Minsky said in his Turing Award speech right at the beginning, he said the problem with computing today is an obsessive concern with form over content. That was in 1970. Sound familiar? So I think there's been a lot. Neil Postman's great book more than 20 years ago was called Amusing Ourselves to Death. It was public discourse in the age of show business. It's a very important, very good book, but if he were to write it today, he would call it Distracting Ourselves to Death, because there's so much more that we're supposed to attend to, and we have fewer resources to reject stuff in favor of what we should be working on. So it could be that computer science education in the US is okay, and I'm just completely missing it. But boy, when I started looking for researchers for this group, and we finally got some great funding last year from some unexpected sources, ARPA, old ARPA without the D level funding, to do a project that has almost no chance of success, and it's going to take us 5 years to fail. I naturally looked for people that I thought would be the right kind of people for this, and I can tell you that virtually none of the people in the group so far that I found have been American. Now, the good news about the internet is it gives you access to everybody in the world, and I've had to go pretty much everywhere in the world to find people. Person from Brazil, a couple of people from Japan, a couple of people from the former East Germany, and we have some Americans in it, but it was striking that the outlook, and outlook is what you need when you're doing research, because you really don't, the whole difference between research and engineering is in part that engineering you're supposed to apply what you know because you don't want that jet plane to fall, right? You just absolutely do not want any scientist or mathematician designing your airliner, because they're even happier if it falls. You'll learn something. You want serious pens in the pen holder engineering when you're flying on that plane. And I don't know if you ever contemplated that jet engine that's out there. I love jet engines, but the more I found out about them, the more I wound up loving them, because I still fly. But it's amazing that they work, and it's amazing that they really work. They're just amazing pieces of technology. But research isn't like that. Research, you're basically, at best, trying to get the tree to fall in some direction so you can run along the trunk for a while. And so you need people who have a very different outlook about things, and essentially people who can be profoundly dissatisfied without getting the immobilization of depression. That is what research is, and most art has that characteristic. Successful artists are profoundly dissatisfied, but they found a way of getting past just being depressed. So they have a feeling, and sometimes you can convert depression into anxiety. Anxiety works because you're active when you're anxious. So basically you're looking for people that, and it didn't seem like the US is turning out that many people, and certainly not university people. The Japanese that I got were not Japanese from universities. They were from the counterculture in computing in Japan, which is awfully interesting and awfully good, but not a product of the Japanese university system. So I guess and I'm also an adjunct professor in a bunch of places, so I've had a chance to look at what's going on, and I occasionally teach a course in university. And my impression is that it's not whether the kids are smart enough. This is something, smart in a sense is easy. But imagine if you had an IQ of 500 and were born in 10,000 BC. How far are you going to get? You're going to be able to outwit anybody. But take a look at Leonardo, who I'm sure is smarter than every single person in this room. But he couldn't invent a single engine for all these vehicles that he wanted to make. He just was living in the wrong time. It doesn't matter how smart you are. And so I think the smartness you're going to find, and knowledge obviously dominates IQ, but in fact, people have been knowledgeable for 200,000 years about something. That's why we survive. We have cultures for knowledge. Every culture is loaded with knowledge. So I think the most important thing is outlook or perspective or epistemological framework. Those are things that schools should be teaching. So the basis of Montessori education, she said, the number one thing we should be doing with young children is getting their common sense to be the common sense of the 20th century, not the common sense of the 11th century, right? And so that is the most difficult thing to find when you run into a high school kid or a college kid. Their common sense couldn't be more alike a cave person.
Can I ask a question?
Yes.
I don't want to distract your flow too much, but
Oh, please.
just to clarify to this audience, I mean, we do research. I mean, there's thousands of computer science conferences. We put out PhDs every year. Those PhDs go to these conferences and present their papers. We're very successful in doing that.
Yep.
But in producing brilliant researchers and all the other universities doing the same thing. But you're saying they're not the people you want for what your approach you're taking, that you need to go somewhere else.
Well, what do
so
you?
maybe you could just tell us what it is that you're.
No, I'm more interested in hearing what. I'm really happy that you broke in, because I will talk forever.
Okay, I'm trying to connect the bridge this thing between what you just said and the
Okay.
fact that what we do is,
Well, here's what
there's an established field of computer
okay,
science.
so when I come to a university, here's what I see is, in fact, people have them right now with them, but when I go into offices and go everywhere, with just a few exceptions, I see people trying to do, presumably research has something to do with the future. I see people doing their computing on machines of the past and software of the deep past. And that's quite normal to people. It's not remarked about. But you have to realize, when I was in school, every university of any note made their own computers. And the students helped make them and design them, and the students helped make up new operating systems for them and write them. And today we live in a time when it's easier to make a computer than ever in history, and yet I don't know of a major university which is doing anything like that. And
We don't grow our own food either.
yeah, and what is that? That's an interesting statement, but I don't.
Well, building computers isn't interesting anymore.
Oh, yes, it is. So let
why
me.
should we do that when we
Well,
can
it's
figure it out?
let me give you two reasons. One interesting one is that Butler Lamson, who I think you'll admit is a fairly smart guy, took a look at the general computing resource at Xerox PARC and compared it, this was done a few years ago, and found that the computers of today are, in absolute terms, 1,000 times less efficient than what was done at Xerox PARC. And 1,000 is 2 to the 10th, and 10 doublings at a year and a half apiece gives something like 15 years of computing that we've actually lost. And so there's an old wives' tale that Moore's Law and the Turing tar pit will make up for bad computing. But in fact, what you're missing, I think, just my opinion, is, and what you're not curious about, is why was PARC so successful, and why has there been nothing quite like PARC since then? That is, why is it so derivative today? And one of the reasons is that we made a computer that was literally 15 years ahead of its time, and thus we were always computing. We had two things going with that computer. One was we made 2,000 of them. So we didn't make just one or two. It wasn't a demo. It was actually a facility, because we didn't want to be bound by vendors' thoughts of computing. And it wasn't just a faster computer, it was a different architecture. And so the two things that worked there were, first, we could try out zillions of experiments without doing any optimization. So we could go out and drink a few pitchers of beer at lunch and come back and do a dozen experiments in user interface and never have to write a line of code that was optimization, because the Alto would just do it. So it was about 50 times as fast as a time-sharing terminal back then.
Can you clarify what you meant by 1,000 times slower than before?
He said less efficient. I'll give you another measure. I'll give you the measure that we did in just a second, as soon as I finish this thought. And so the other thing, besides not having to optimize to do a zillion experiments, this helped us a lot, because for us it was hard to have a good idea. The way we thought of it is, boy, it's easy to have mediocre down to bad ideas, but it's really hard to have good ideas, because we just don't know. There's not a lot of principles that are worthwhile in computing. Therefore, we have to do experiments. And doing experiments without having to optimize was huge for us. Not just in the user interface, which is critical, where you're doing hundreds and hundreds of things and trying them out, but also just in programming languages and other areas. But the other thing that was very, very useful was that if we were willing to optimize something on the Alto, then we were writing code like people were going to write 10 years in the future. In other words, we could make an actual application that would be comparable to what was going to happen 10 or so years in the future. For instance, Microsoft Word was done 10 years in advance of when it actually came out, precisely because we had the computing horsepower to do that. So both of those things were absolutely critical to allow us to live in the future instead of the past. Everybody else in the country had computing resources also, but they didn't realize, like McLuhan has pointed out over and over again that all of these things have built-in resources. Now I'll address your thing. So here's a benchmark we did, which was more conservative, I think, than Butler's. Although Butler is a much more conservative guy than I am, so I was very surprised at his factor of 1,000. But we, it just turned out that our research for convenience was built on a version of the software we had done at Xerox PARC because it was easily portable. And so we had optimized it on Macintoshes and on Windows Intel processors with about the same amount of effort as we had optimized at Xerox PARC. And so just for the heck of it, we ran some low-level benchmarks that we happened to have figures from back at Xerox PARC, and they were only 50 times faster. And when we worked through the various Moore's Law things and the clock speeds and the other kinds of deals like that, we thought, boy, there's a factor of 600 missing here somewhere. Where did it go? Now, Butler has a talk that he gives. You should invite him here to give that talk on where he thinks it went. And, but in fact, if you actually look at the thing in a finer grain, and actually I have a slide in actually the talks I gave in 2004, I even showed that slide here, showing that things really haven't sped up as much as Moore's Law claims it is. Because, for example, the memory architectures today are abysmally slow. They have no correlation of any kind with Moore's Law, almost zero. The caching is done so inefficiently in several different places today that it has almost no connection with any Moore's Law. So there's a bunch of things that have no connection. And the PARC hardware happened to be microcoded. And so we designed it explicitly for doing very, very fast virtual machines for very high-level languages that would keep main memory busy. Not contending with main memory like any virtual machine that you do today, but it was these emulators were made so that they ran independently and much faster than main memory, and were able to, if you could keep main memory going, our theory was you couldn't do any faster with just gates. And so our whole approach was very different. And so the speed up is not a speed up in clock time, but it was a speed up in, to the user time. And the low-level benchmarks are really surprising to me because I would have expected those at least would have been faster. But in fact, they weren't. Yeah, sorry. Somebody down here had, yeah.
So, two-part question. The first thing is when you're looking for your team and you're trying to figure out who to bring in, what things are you looking for in them that would cause you to bring them in? And the second part is, if you were to create a school to train people that you could bring in, what would you use to decide who should be in the school?
Well, the second one I don't know. The first one, basically, I mean, generally speaking, I've over the years, and the old community over the years loved intern programs because, and partly because, for instance, I never would have been accepted into graduate school if David Evans looked at transcripts. But he didn't. He couldn't care less about transcripts. And so he did look at resumes. If you'd done anything that was, if you had on your resume two things that were in direct contradiction to each other in some way, he loved that. And so after I got my PhD at that ARPA project, I was on the faculty there for a year, and I got a chance to see how they did it from the inside. And so Dave's theory was anybody who's remotely interesting, let them in. Don't bother debating or any of that stuff. And give them 2 years. And then get the faculty together, and every single person had better know every single student. That was one of the rules at most of the ARPA projects. I think here at Carnegie also. And Dave Evans and Perlis were great friends, and so I think the scheme here was somewhat similar. And then the faculty would decide whether this person was real or not after this 2 years. And if the person was decided they weren't real, they would fail their orals or fail their quals and be let out with a master's degree. And if the faculty decided they were real, then they would go on to get a degree. And the way it was done at Utah was 2 years of top quality, world-class quality work advancing the field was a PhD as far as Dave was concerned. So if you were working on a really hard problem, you didn't have to finish. Because there wasn't, if you worked on an easy one, so I was allowed, for example, to write up the work I had done so far on personal computing over the 2 years there, and I was out of Utah in 2.5 years. That was the way they did it. No place I've ever been a professor at, aside from Utah. I've been at Stanford, MIT, Caltech. None of those places would ever accept me as a graduate student because it's more complicated the way they look at it. So, so to me, anybody who shows interest, like I've got this crazy guy who has been winning me over, who is a crazy Australian who's in Kathmandu, Nepal right now. But he found out about this project that we were doing from, he had worked on Erlang, and through the grapevine, this came to, and this guy actually traveled to Italy when I was there a month ago so he could meet me and talk with me. And my thought, and this guy just doesn't look like the right guy, except that now we've got him for a four-month internship, and now I'm thinking he might actually do it because, boy, there's nothing like motivation. My worry about him is that he might be too much of a hacker to work in our project because we have to do some deep stuff. And what we're going to try and understand about him in the internship is whether he has some feeling for deep. And if he does, by God, we're going to keep him.
What is your project?
Well, this project is if you go to the in that page, which has various recent writings, is the NSF proposal, which gave us half of this. So this is basically a $2 million a year project. We got $1 million a year for 5 years from NSF, and I found an even crazier funder for the other half of it. So we're doing it, and it's called Steps Towards the Reinvention of Programming, and it's not that easy to explain because it is not the same as reinventing programming, but it's an attempt to get halfway up the mountain. The idea is we're so mired in normal, there's too much normal going on, that we need to do something to at least carve out a base camp that we might be able to see a little more about the routes to the top. And so in this proposal, I identified 13 ideas, most of which were not had by us, but over the years that I've thought could be an alternative basis for an entire computing system.
Can you do some of them?
Yeah, one of them is, like when Linda came along, I thought, boy, if Linda could really do pattern matching and if it really ran the speed of a subroutine, that would be really cool, because then you would have publish and subscribe messaging. And if you had publish and subscribe messaging, you could actually have a very different basis for thinking about what programming actually is. And so that's one that's been on the back burner for a long time. And there was an AI system that was based on work done here at Carnegie, some of the Ops 5 stuff. It was called ART, Automated Reasoning Tool. It was done at a company called Inference, but some former Carnegie people. And I don't know, 15 years ago, another colleague and I spent a year trying programs out in this because it had a fast forward inference. And the forward inference on it was fast enough so you could do things that were like pattern-matched, event-driven stuff. And we became quite convinced that if you could actually do the next round of this, it would be a much better way of thinking about doing loose coupling between large numbers of things. So that was just a thing that stuck in my mind about. And now, of course, you know, the CPUs at Xerox were all microcoded, and the modern equivalent of microcode is field programmable gate arrays. And field programmable gate arrays are actually very amenable to 2 or 3 of just changing fundamental assumptions, like, hey, let's get rid of procedure calls. Forget it. Let's try a different way of coupling, and we'll win if we can do it fast enough and the new way actually has something going for it that the old way doesn't. So that's one of these 13 things in there. And the proposal is preposterous, as one of the reviewers, and I believe this proposal actually didn't pass review, though they won't tell me. I believe what happened actually is that they did have money, they didn't like the papers that they'd gotten. I was requested to write this proposal. NSF has never funded anything we've ever done before because it's too risky. And I think they just decided to fund it because it is preposterous. We have every chance of failing on the thing because what we're proposing is to start with gates and get up to the end user with something that is recognizably the entire personal computing experience in less than 20,000 lines of code. So we're just saying, hey, we want a Moore's law increase in software expressiveness, and we want something that's 2 to 3 orders of magnitude less lines of code, and we want that code not to be cryptic. It's not writing everything in half-size APL characters, but to actually, and this isn't the same as reinventing programming, but we're going to have to invent a few things to make this work. And of the 13 things that are expressed in this proposal, a few of them we know how to do better than others. We've been doing experiments over the years. And this proposal found its way to NSF first as a white paper, because when I'm noodling about things, I like to write an essay about it and distribute it to friends for comment. So this essay, which is much longer than the proposal, has been circulating for a few years. And we had been doing experiments in the system we've done for children. We've done a lot of experiments at the end user end on how can you do an entire personal computing environment with just one kind of object. So it's just an infinitely recursible and unbuildable thing out of a much simpler kind of building block than the hundreds of object types that are usually used. So this isn't starting completely off from scratch, but in the middle of this project, there are 4 or 5 of these principles where, you know, that cartoon that has the 2 guys at the blackboard and then a miracle happens. My favorite cartoon. So 4 or 5 out of the 13 things that we mentioned in there are of that nature. I could not tell you how we're actually going to make them work. But basically in a 5, you know, this is a project that if it's doable at all, it's doable in 3 years. But like the dynamics are, if you take a 3-year thing and only fund it for 2 years, it takes 10 years. And if you fund it for 3 years, it's going to take 5 years. But if you fund it for 5 years, you can usually do it in 3. And the reason has to do with the kind of engineering you're actually willing to do early before you start making commitments. And so, you know, we asked for 5 years of funding, but if the thing isn't really convincing in 3 years, it'll be a flop. Right? That's basically the dynamic. So, but I've tried to give talks about it, and it just doesn't fit that well into a talk, even though I give demos. So I think the proposal actually is the least confusing version of this thing. But I think you'll think it's preposterous when you see it. Yes?
In 1985, Alan Moore wrote a paper in which one of the things was billions of dollars for studying compilers and pennies for studying the programmer. In a rational science of programming, there might be more balance. Does that fit into your thinking? And so,
Well, yeah, in the sense that humans are usually their own worst enemies about everything. And like, here's an interesting one. So I was a professional programmer for 5 years before I got interested in computing. I just learned how in the Air Force, and I put myself through undergraduate school and 2 other degrees writing programs for the National Center for Atmospheric Research. And so I didn't realize computers were really interesting until I accidentally found my way into grad school. And I think the thing that, when I look back on that, and when I look at most programmers today, and when I look at computing today, the thing about programming is, if you're going to be successful at programming, you have to be good at coping, right? Because you're always working on, it's almost never do you have a chance to do anything from scratch. Somebody else's machine, somebody else's software you have to go on, somebody else's compiler, somebody else's blah blah. And you know what? The better a coper you are, the less good a programming designer you are. Because the whole art of designing a programming language is partly being physically ill in using some programming language that you decide is ugly for one reason or another. And basically, if you're happy to cope, so one of the rarities of the people I look for, and the rarities at Xerox PARC was full of people who were awfully good at making things, but also were awfully good at being critical. PARC was a frightening place to visitors because we argued all the time. And the arguments were about why this is shit and why that's shit and why our own stuff is shit, everything is shit. And how can we get out of this shit? And so that's difficult. Today it is very difficult to, if you complain today, first I think the internet has done away with criticism in the sense that, like Gresham's law, it's driven good criticism away. There's so much unfounded criticism on it. So good criticism, any criticism is put down as a rant because so much criticism does not have anything behind it. So I think it's very difficult to criticize, get away. But also, again, when I was traveling around in 2004 giving talks, the predominant attitude I had was a misconception about Darwinian processes, that most people I talked to thought that we must be at the best place that we could be, because look at how many millions of people are participating in this thing. And if you know about Darwinian processes, they aren't optimizers at all. They're satisficers, a term made up by one of the most famous professors ever to be at Carnegie. And satisficing is not the same as designing something great. Yes?
So I must have misstated my question.
No, I'm sure I elliptically answered it.
So Alan was advocating actually studying programmers and what they
Yeah.
do and how people think, to inform the design
Yeah,
of
so I'm exactly,
languages and
okay, so that's, I'm really glad you put it that way because I couldn't disagree more. Because I think that, so the rallying cry for these high school teachers tomorrow, but it was also the title of the talks I gave a few years ago, was the computer revolution hasn't happened yet. And if you subscribe to that, then the last thing we want to do is do any kind of analogies and trajectories from what's going on today.
I absolutely agree with you. What the better word to put in there besides programmers is your target programmers.
Okay, my
studying them and
yeah.
how they think and how they
Yes.
think.
Well, then I couldn't agree more because, well,
And I agree with you too.
no, it's just like, to me, the most important, so, PARC is falsely credited for inventing the GUI. Nothing could be further from the truth. There are plenty of GUIs in the 60s, but the thing that we did differently there was that all of the GUIs in the 60s, almost maybe with one exception, were command and control GUIs. And as they thought of the purpose of any user interface to be like the panel of a nuclear submarine or reactor, which is to give you access to functions. And it was expected that you would be trained to use these things as you are in those cases. In fact, that has come back. That's kind of where we are, but in part because we included our users to be children. So we said it's not personal computing unless children can do it, because for the very same reason it's not a printing revolution unless children can learn how to read, and et cetera, et cetera. So because we were thinking along those lines, we thought, oh, it would be more interesting if given that the very nature of a computer is to go beyond what it already has, so that if you can do something on a computer, that doesn't limit it. You can also do this thing and you can do that thing, and many things are going to happen if this stuff ever gets commercialized. So our idea is that first and foremost, the user interface has to be some kind of learning environment. And because most of the functions that you're eventually going to get access to aren't even going to be there when you start. So it has to have some theory of how you learn these new things. And in fact, you could say that what's limiting much in the user interface domain today is that the user interfaces are so, and the applications are so non-set up to teach people things that they feel like they're forced to use old conventions in the user interfaces. So it's only in areas like video games, for instance, where the children really want to use both hands, for example, whereas most adult applications are not two-handed interfaces. Precisely, well, but I'm saying that that's a different way of looking at it. And the way I look at programming is that it is every much as important and in the same philosophical domain as reading and writing and math and science. And that the main goal of education is not to try and produce professional readers and writers or professional mathematicians or professional scientists or professional computer people, but it's designed to produce people that are more enlightened than they were 100 years ago, because they have an additional set of ways of thinking about things and expressing them. Right? So that was the basic zeitgeist of what personal computing and networking meant in the 60s in the ARPA community. That was the whole big deal from Licklider's first paper on, which was not about how computer people are going to interact with computers, but about how everybody is going to be able to enjoy an intellectual amplifier for their endeavors. And so what does that mean? So from that standpoint, the last person you wanted to study is a person who does well at programming today, because by and large they're doing well at something that was quite recognizable before 1965, including the amazing thing that most people still do system builds once a day, which I thought had gone out a long time ago. Yeah.
So what activity would you study instead?
Well, so people come in different flavors. To me, the most, and I hate to be prescriptive, but if there were one thing I would try and get every child in America to deeply embed from around 5th grade through the end of college, it would be anthropology. Because it is the best way of not taking yourself and your culture too seriously, or any of the subcultures you're involved in. I think it's the most important thing. And in order to understand modern anthropology, you have to understand modern biology. And modern biology is probably the best, well, pound for pound anyway, I would claim modern biology is the best thing that we should be looking at as far as scaling and going from strongly coupled things to weakly coupled things. Remember, computers started out as being a kind of a 16th, 17th, and 18th century kind of idea, kind of like gears, kind of like old style mathematics. the algorithms are kind of gear-like, and the idea that you can smash values and data structures and get away with it implies that you're thinking small, right? Because that doesn't scale. And so to me, the most interesting artifact from the 70s, and pretty much the only ones that have survived almost untouched to this day because there weren't alternatives, were the internet and the Ethernet, both invented by the same community, the ARPA community that Carnegie used to be part of. And if you look at why this works, you see a direct contradiction in you can write down 25 things that the computing culture believed before the internet that are contravened by the internet. Just in every domain, and it's a really good exercise because the thing you realize more than anything else is that a paradigm shift happened. And of course it happened in other places. And if I had to sum it up with a word, I had to come up, you know, what am I going to say to the high school things? I would say that the ARPA PARC research community, if you had to come up with one term for what they were thinking about, it was no center. No center, which means networks are not star networks. You have personal computing. Everything is distributed. You have distributed objects, and the objects don't have a center. You have no programming language. You have no applications. You have no operating system. So all of those things were experimented with at Xerox PARC. Right, so yeah.
So the decentralized architecture is quite a romantic idea, and everyone seems to like it. And
it's hard to tell. The last time I looked at the task manager on my Windows operating system, I only saw 30 processes running. Am I missing something?
well,
I would expect to see my little your little laptop there is the equivalent of the entire internet in the 80s sometime. Right?
Yeah.
Computing, storage, processing power, everything. And when I look inside it, I would expect to see a few thousand objects with no center,
right.
not tied to any particular operating environment. Why should they be? Right? What's
Well, let me
So,
actually
yeah.
suggest why. And like, because this 100,000 times less efficient in absolute terms is kind of bothering me. I mean, as a developer, I know about coping with legacy code, and so like that seems to be like, it seems that we can't. It seems like we're doomed to get mired in this proliferation of shit, as you were talking about earlier.
You aren't doomed.
Well,
That's my message.
no. Well,
But don't follow me.
Are you saying that we need a standards body to enforce?
No. So they
Go around and clean up everyone's bad designs?
no, look. So let me just sketch. So here's something. Suppose let's take the internet seriously for just 1 second. So, and I love talking about it because I had almost nothing to do with it. I had something to do with the ARPANET, but the internet was done by colleagues of ours, and so it's not like claiming that Smalltalk is better than Java, which would be a bad thing to try and do. But since I had essentially nothing to do with the internet, I can praise it to the skies. And so let's just look at it abstractly for a second. It's maybe the only real object system on Earth where each object is an entire computer. There's nothing more encapsulated than a piece of hardware, right? And pure messages are sent to it, really pure. So one of the most interesting things about the internet is that if an object that receives a message is going to crash as the result of that message, it was its own fault. Right? Because we're not sending 100,000 volts over the line there. We're just sending bits. Those bits are entirely interpreted by the programs on that object, and the object gets to decide what to do.
So do you think every developer should be his own object?
No, well, wait a minute. So let me work it a little bit further. So then let's suppose we could do that efficiently in smaller things. These are the thoughts I had in 1966 when we were trying to think about some of these ideas. But so the thing I love about the internet is, boy, if I need something, there might be some object out there that could supply it, and it might be able to be of service to me, and I don't care what operating system it's running or any other thing, right? Because it's a pure messaging system. So I may be doing one kind of thing, and that guy over there may be doing some other kind of thing. I don't give a shit. And so then the next thing I want to do is I somehow want to get as many of those objects in my machine as possible. So the first thing I would talk to our friends at Intel about is, why don't you understand virtual machines? Like, the most important thing you can do on a computer today is confinement. So let's have it cheap. Let's use some of that memory that you're using badly for doing caching wrong. Let's use it so we can have thousands and thousands of virtual address spaces completely inexpensively on there. And if you do the math on it, it's absolutely possible. It's just not architecturally in Intel's mind. Nobody's ever explained to them why this would be a good idea. Then all of us, and why don't we make inter-process messaging really fast instead of really slow, the way Intel does it? And all of a sudden, you actually start thinking, oh, wait a minute, I don't need an operating system. Because what I really want is facilities. I want services. And I must have confinement because things can be dangerous. But I don't want to rely on software for that. I want real confinement. I want to be able to get anything from Timbuktu that looks reasonable, and I'd want to chuck it into a virtual address space and absolutely confine the shit out of it. And I want to do experiments with that thing. I want to feed it things, and I want to see what it feeds back to me. I want to be able to use it in various guarded ways, et cetera, et cetera, et cetera. These are not new ideas, but they are like magic if you try to explain them to Intel. Because Intel could not even get to the point of allowing programmers to microcode, so you can do higher level languages. So what I'm saying is the level of retrograde here is really back before 1965. But it helps to have been in computing before 1965 to see it. Because today, for most people, it looks normal. And from my standpoint, my goodness, the normal, like before 1965, there was a computer called the B5000, which, believe me, every one of us that runs higher level languages would much prefer Intel to put on their chips instead of having to emulate it as we do. Every byte encoded virtual machine in the world is imitating in software this thing that was directly in the hardware of a machine in 1961. And this is why I say we don't have a field. The reason we don't have a field is because none of you know this. And if you're in physics and you didn't know about what Newton had done, remember, Newton was 400 years ago, and the physicists make damn sure we know what Newton did, and they should. But computer people, when they teach other computer people, they don't make you know what Bob Barton did or what Engelbart did. So when I was traveling around in 2004 giving talks, I got a lot of pushback when I said, well, maybe computer science is still an oxymoron. You should have seen Perlis would have thought that was really funny, because that was the whole point. It was an aspiration. But today what I got is from every computer science professor, bullshit. This computer science is real and it's what we're teaching. That's a field that has failed. Absolutely failed. So what I started doing in 2004 was to ask computer people the following question. Have you ever heard of Engelbart? Yep. What did he do? Well, didn't he have something to do with the mouse? And then the key question was, have you ever typed Engelbart into Google? You don't have to go to the library. You've got it right here. You're sitting right here. Type his name in there, and what are you going to find? In the first page of hits, you're going to find access to the 75 papers that Engelbart wrote about some of the most profound issues in interactive computing with people. And you'll also find there the videos of the Engelbart demo in 1968, of which next year is the 40th anniversary, and the World Wide Web is still not up to many of the things shown in that demo. And part of the reason it's not up to it is that nobody even knows about that demo. So it is impossible for me, having come out of math and molecular biology, to take computer science as a field seriously. The people in it are not acting like it's a real discipline. A real discipline actually builds on the past. And our discipline is trying to build on IQ. We're like cave people back in 100,000 BC without any real knowledge, trying to outsmart the other flora and fauna in our environment. And it's worse today because the web has given rise to a pop culture which couldn't be less interested in the past or the future. They're only interested in identity. So at a university, so to me, there's always too much knowledge to teach. So the primary purpose to me of any educational institution is not to teach. That's just being completely arrogant to think you can teach. The purpose of any educational institution is to help the students understand where the thresholds are in quality. When is what you're doing below the threshold is basically air guitar. It's got all the trappings, looks like it. When is this paper you're writing meaningless? It's got all these mathematical symbols in it, but does it have anything to do with computing? Does it have anything to do with advancing? Does it have anything to do with inventing computer science like it should? And if it doesn't, it's the job of the university not to compliment the student and the professor because now they're going to get tenure because they've written, this is their 10th paper, but to say no. Quality standard is here. Below this, it's not a real discipline. It's not a real science. It's not software engineering below this. It's just bullshitting around. It's just going through the motions. So the thing that, to me, the biggest difference I believe I see, I could be completely wrong here, but boy, the ARPA-supported universities in the 60s, that was their deal. It was all about when an idea really constituted an idea, and when, like, you couldn't get a PhD in the ARPA community in the 60s without advancing the state of the art in some material way. They just wouldn't give them out for any other reason. I mean, what if that were made a criterion for a PhD? We would have flight from the universities. I wish we would, because I think all of the computer science departments are too large. In the late 70s, there was a huge battle in the ACM. Some of you may remember it. You might remember it. And the battle was about what shall the undergraduate curriculum be in American colleges and universities. Because remember, there were only a few places that gave out degrees, but there were 4,000 degree-granting institutions, and they were all starting to get interesting. So in the late 70s and early 80s, there was this incredible battle, and from my standpoint, the bad guys won, in that they went all the way back to, basically, to Algol, Pascal in this case, to algorithms and data structures, and completely omitted the idea of the internet, that is, systems were starting to become much more interesting than algorithms. And systems thinking you don't get to by doing algorithms. It's much easier to do algorithms in the context of system thinking. Some complicated thing, but trying to scale up algorithms, you get 100 million line operating systems like Windows XP. You just don't, they're just two different paradigms. The big one includes the smaller one, but not the other way around. And so this thing actually, I believe, changed computing history, because people started turning the curriculum crank. And to this day, I was asked a few years ago to look at both AP and the undergraduate curriculum standards in America by the National Academy of Engineering, and boy, it looked awfully familiar. It looked a lot like the kind of programming I did in 1963. Yes?
So So what you're saying sounds to me like something that I've often thought is that we're maybe trying to teach the architects and the stonemasons in the same classroom. And I'm wondering, and that costs us a lot in terms of teaching outputs, if we're teaching individual technologies and teaching the skills to be professional programmers rather than perhaps researchers. So I'm wondering, what would you think about the idea of teaching professional programming as a vocation and teaching computer science at a university?
Well, it's interesting that historically that's the way so when I started programming, it was in 1961 in the Air Force. And actually my boss was a woman, because you may not know it, but a very large number of programmers in the 50s were women. They got pushed out when it became a popular profession. But it was actually, and in Japan, it was a low-class profession for quite a while. So so my boss was a very talented woman programmer. And it turned out that a programmer in those days was a person who made flowcharts. And the person who wrote the code was called a coder. So I started out as a coder, implementing other people's spreadsheets. And this was a predominant way of going on. So the architects were one group of people that were figuring out how this stuff would work, and then they would have a bunch of people that would write parts of these things. But I think that if you look, let's look ahead towards a benign future. So the other way of looking at it is, wait a minute, why shouldn't architectures need to be debugged also, right? Certainly nobody in this room believes in specifications that you can't run. I hope. Because just think about it, anything you write in any language is going to have bugs in it. So, so the question is whether you can make up an architecture that is simply the prototype for the system, and what you have instead of architects and programmers is you might have something more like architects and optimizers. Because I believe there's a difference between design and optimization, and it's hard to do both at the same time. If you've ever, once you put your optimization hat on, it is awfully hard to design because you're just in a different world. And one of the 12 principles, by the way, in this thing is to make a system in which the meanings of things and the optimizations are 100% separated, and to make that work in a practical way, so that you should be able to write an entire system in terms of the meanings you intend for it, and to be able to debug it and check it out. Maybe you're doing it on a piece of hardware that runs 1,000 times faster than where you're eventually getting to, but basically to make that part of it stick. I don't know what the answer is, but I think that, to use your metaphor, computer science has almost been colonized by the stonemasons, in the sense that they are in every university department in the country. That I can't identify too many architects in academia today, because architects do architecture, and where are the academic institutions today that are actually making things that require architecture? Architecture is not a theoretical deal. You have to make it in order to understand it. So I'm not sure that but one of the maxims is that architecture dominates materials. So if you just take bricks as they come, you get walls and piles of them, which eventually become pyramids and things. But the arch is an unusual organization of bricks, hard to think of. The Greeks were very smart and they didn't invent it. And so literally arches give you architecture, right? Architecture means the making of arches. And I would say that a 100 million line operating system is building something without an architecture, because it's just aggregating. And the big problem with building a pyramid with arches and without arches is not just the 1/1,000,000th of material you need if you make the pyramid out of arches, but it's the pyramid with arches is also reformulatable, and the one without it is essentially not. Right? So all of those things I think are really very important, but I'm not sure you can teach it as late as college, because again, it's a form of, I think it has some paradigmatic things to it. It's a way of looking at the world, and if you want people to look at the world in ways that cave people didn't look in the world, you need to start early with children and get them to have some appreciation for scale, for example. Yeah.
Have you talked to Jeanette Wing, or not just her, but a number of different people have proposed this computational thinking
Yeah.
as a way of something we should be teaching, and I think their view of it is that the great inventions of computer science that we had over the last 30, 40 years, whatever, those ways of thinking ought to be imbued to the rest, to everybody. But that seems to be the opposite of what you're saying. You're saying our field is garbage, and we should, and nothing of value really has come out of it, and we're all going the wrong direction.
No, here's what I'm saying.
Okay.
What I'm saying is I love computing more than anything. Else, why would I be here? I love it. It's one of the best inventions human beings have ever come up with. So there's nothing garbage about it. But I feel really sad, to a depth I don't want to confess, that people aren't taking advantage of the wonders that it has and are not even curious about the wonders that it has. I feel profoundly lucky to have been in my 20s and 30s when I was, because the other thing about it is that the field isn't there yet, and what it means is that looking into the future isn't just a bunch of slogging and making footnotes on the past. It's not even close to that. But in order to, in a sense, McLuhan said, we are rushing faster and faster driving faster and faster into the future, but steering only by looking at the rear view mirror. And another wonderful line he had was that, he said, most people can only deal with the present in terms of the past. So, but artists can actually see a little bit, and the reason is the present, we are not aware of how many things we've normalized inside of ourselves that we take for granted. And artists are people who can see that a little bit. They can see it a little bit, and because they can see this is what they report in their art, is what is actually going on. This is what McLuhan was reporting, was actually what was going on, not what people thought was going on. And because of their ability to see a little bit of the present, they also see a little bit of the future. Susan Sontag said, all progress starts with our refusal to accept something about what's going on today. So part of the deal is to just, see, and I don't believe we're trapped for a second, because, for example, when Nicholas Negroponte decided to do the $100 laptop project, a bunch of us got together and we raised $20 million, and Nicholas went out and started getting countries signed up. And the truth about laptops is, I don't know what kind you have, but all the HPs, all the Dells, half of the Sonys, and a third of the Macintosh laptops are made by a single company in Taiwan called Quanta. They have a different factory for each one. You have to have a different badge to get into each one, but they make 42% of all the laptops in the world, and if you want to make a laptop, or any university wants to make a laptop, you just have to get on your CAD, much easier now than it's ever been in history. You can debug the whole damn machine before you have to build a single atom of it. Take those plans over to Taiwan and they will build you a machine. I mean, when we did the Alto, we had to set up a production line. We could build maybe 3 Altos a week. It took us a long time to build 2,000 machines, but today, Jesus. And that project started in January 2005, and we made 1,000, and we had to invent a new kind of display for it, because the way displays are done today are too expensive and they don't work in bright light and in darkness. So we had to do a whole bunch of things. By the way, a very, very talented woman scientist is the CTO, Mary Lou Jepson, a true genius, was able to invent this display, engineer it, and in less than 2 years after the $100 laptop project started, last November, we ran 1,000 machines through the factory, with 0 defects on the display. First, never been done before in history to do that, and it was like 15 or 20 people.
And they're hand cranked.
No, they're not hand cranked.
No, they're not.
Go get on the internet and find out what it is today. You're dealing with stuff
I'm
from...
talking about the UN deal with the...
Yeah, that was like in 2005. This is 2007.
Oh, sorry.
Yeah, that was a bit of a gimmick.
Yeah.
But the cranking is now, you know, as we thought it would be done with a treadle, because that's, most things are treadle powered in the third world. And there's also a really beautiful, efficient thing like this that has a flywheel that will generate. And the $100 laptop, even with the display lit, draws less than 2 watts. The display lit and the radio goes 24 hours a day. So the network, it acts as a node. It's actually like a radio version of the ARPANET. And so even when the machine is off, it's acting as a retransmitter for the other machines in the mesh. But I mean, it was not a hard thing to do. It was like 15 people to do it, and some willpower, and basically not saying we're trapped in X, Y. Trapped? Come on. This is the easiest time to make anything in history, whatever it is. You can make a jet engine here at Carnegie that would really work if you want to. There's nothing you can't do. But the problem is nobody wants to do it. That's the big, yeah.
When you mentioned Neil Postman, I got excited.
Okay,
Then
well.
when you mentioned amusing ourselves to death, I got more excited. And so I want to bring up E.E. Cummings. Okay, because I think of E.E. Cummings as a pathway to get to the next level of computing. And I think what he did with 10 lines of nonsense and a couple of commas and semicolons to get someone to actually understand a big idea is, like, we have so much communication, we have so many programs that do the same old thing over and over, it's boring to use the computer. But if the computer could be somehow more integrated into life where it's actually useful and more intelligent and more able to help us arrive at these revelations, so to speak.
Yeah.
And I really think some kind of a study into what makes a person get it as opposed to not get it.
Yeah.
When they look at something by E.E. Cummings, just as an example,
Yeah, well,
is a kind of direction that
He-
a person
he and-
wants to go in, but poetry is not promoted in the community.
well, this is why McLuhan was famously difficult to understand by most people, because he used a similar technique, the same technique that Zen uses, which is to express things as paradoxes. And so if you have two things in opposition, you can stay in 2 dimensions, or maybe 1 dimension here in opposite, and keep them in opposition, or you can find another dimension and suddenly you get a nice thing like an arch. So a lot of things that are paradoxical are worthwhile mulling, because usually they're an escape into a different place where they're not paradoxical at all, but they actually work together in some way. And this is why, basically, I respectfully disagree with what you were saying, because I think that essentially what's happened is the theory about normal and also the economics involved. Like, it wasn't that long ago that researchers at Carnegie and MIT and other places were sitting down to machines that cost $80,000, $90,000 called workstations. And they got to peer a little bit into the future on those workstations for a bit. But basically the economics now has gotten everybody to not be willing to pay even 1/10 of what they're willing to pay for their car, for their computer. Now, if somebody would make a computer that was actually $20,000, $30,000, like my car, I would buy it in a second. I want that factor of 10, because it will help me in the future. But so here's an interesting thing for people who are, don't want to do this all by themselves. Chuck Thacker, who is the great, should be given a Turing Award, but the ACM hates hardware people. Never given a Turing Award to a hardware person. Even Maurice Wilkes, who was a hardware guy, got it for a software thing. So this is absolutely outrageous. But Chuck Thacker was the architect of all of the computers at Xerox PARC, and he has been working with Dave Patterson. You've heard of him. And this summer happens to be maybe the turning point in field programmable gate arrays. So it's, if not, then next summer. But we're right at the cusp where these things are going to become a huge weapon and within reach. And Thacker is designing a modern day Alto computer, which probably half of it will be field programmable gate arrays. But our definition of a research computer is it's 2 cubic feet of the fastest hardware on the planet, constant, right? So every 3 years you have to clean out the 2 cubic feet you got and put in a new 2 cubic feet, and then you can actually do research. And so Thacker is arranging so that this machine is going to be made by a Silicon Valley company and will be available for sale for people who want to actually do research. You know, this is part of a discussion that a bunch of us have been having over the last bunch of years is, hey, where are all the wedges? Well, big wedges are in people's minds. People just can't imagine what computing can be if it isn't like what it is right now. But the other wedges have to do with, in order to get ahead, you have to have some way of peering into the kinds of, you have to have a way of making systems. So like another one of the things that we're planning on doing with these FPGAs is experimenting with these thousands of protected address spaces so that you can actually build a thing that is not an operating system that is much more scalable and flexible, et cetera, et cetera. Yeah.
Last question. Unfortunately, we're running out of time. Go ahead.
I agree with a lot of the things you said about there being a lot of silly ideas in computing that's currently being used, and there's a lot of better things to be done, and there's a sense of being trapped in those conventional ideas. But as a researcher and seeing research on industrial labs and academic labs, it seems like the biggest force keeping the sense of entrapment is mostly marketplace forces, like just what's commercially viable. And so even at Microsoft Research, I saw a bunch of ideas which were great ideas, but they weren't being adopted in the product because they wouldn't sell or they're too experimental.
Yeah, but
so what's your thought on?
well, my question is, what does research have to do with marketing?
Well, the money comes from
No, but what does science have to do with marketing?
science needs money to run on.
Yeah, and does it need it from companies?
It's a big source of it, unless, well, I mean, especially like.
Well, it's not a real, look, it's not a real source of it if there are too many side conditions. If the side conditions take the science away, it's not actually research money, right?
But there's also the prospect where, the aspect where you have a good idea, but it's too different from what's existing in the market, so it doesn't succeed, essentially.
Yeah, but you ever, okay, so I think it'd be worthwhile introducing people to scientists of the past and why they did science. Because I think, see, I persist in using the actual definition of science for science, and I refuse to admit a different definition for science as applied to computer science. And believe me, science has to do with advancing knowledge and and unearthing powerful ideas. It happens to have benefited people who like money incredibly, but it has nothing to do with them. Nothing. I think you might be talking about engineering.
Well, for example, if you were talking about this distributed operating, or lack of operating system, and distributed services type of environment on
Yeah.
a laptop computer, the installation of Microsoft Windows will prohibit such a system being.
But I couldn't care less, because what I have to do is to make a working version of this thing that,
Prototypes are easy, or relatively easy.
Okay, well,
But it's in terms of like having, improving the state of computing in the world and its perception.
well, I have to get you to lead me to all of the interesting prototypes you know about.
With that said,
So I think I had this conversation the other day when I was at UCLA with a kid who kept on using computer science, but was really talking about engineering. It was just a word to him. It never occurred. He didn't actually understand what science was all about, and that's part of the problem, is that maybe the final word is we've let the imposters into the temple. We've gone to something that is more like a Christian Scientist hospital. It's
that may be the last word.
and there's nothing more uncomfortable than being a physician in a Christian Scientist hospital.
So with that said.